So welcome everyone to our webinar, Opportunity for Optimization in the Telecom industry. We are going to review two cases today, network planning and data monetization. For Gurobi, as a leader in the mathematical optimization space, it is a pleasure when we have the opportunity to present along with Baobab, a premier partner that delivers analytics solution, prescriptive analytics solutions, but also have a unique and a vast expertise in the telecommunications industry. Today, leading our webinar, we have with us Julio Lema. Julio is Baobab's business director. He's a telecommunications engineer with more than 20 years in the industry, and who is currently obsessed with bringing mathematical optimization to the telecommunications worldwide. Also joining us is Esther Fernandez Bravo. She's an operations research expert at Baobab. She has participated in a number of projects in the transportations and the telecom industries, and she is actually a student in finalizing her master's degrees in industrial engineering from the University Politécnica de Madrid, and she was also top of her class in her bachelor degree there. And finally, Guillermo Gonzalez Santander. He is a project manager at Baobab Soluciones. He is a master and an expert in artificial intelligence, and he is focused on bringing innovative solutions to complex real-world problems. And what a best opportunity than this one to present those complex problems in the telecommunications industry. So Julio, Esther, and Guillermo, welcome to today's webinar.
Thank you very much, Silvana. It's a pleasure to be here. Hello, everyone. My name is Julio Lema. I'm business director for telecommunications at Baobab Soluciones. Before we start with the use cases, let me introduce you. Let me tell you what we do at Baobab. Baobab is a small consulting firm based out of Madrid, Spain. We are specialists in customized, tailor-made advanced analytics solutions, namely prescriptive analytics for medium and large organizations. What we do combines technology, data, and intelligent analytics to help a wide variety of industries achieve unprecedented efficiency and productivity. Our solutions are based on artificial intelligence, big data, and operations research, and they have contributed to creating added value at a strategic, tactical, and operational level in a multitude of industries and business sectors. Just to name a few: production and manufacturing, logistics, supply chain, retail, and now telecommunications, where we have partnered with telcos such as Orange to enrich their digital transformation and AI portfolio with our tailor-made solutions, bridging the gap between the insight and the decision. In this webinar, we will show you two examples of how telcos can benefit from optimization and the use of Gurobi. In one case, to the reduced OPEX and CAPEX of the networks, and in the other one, to unlock new revenues by monetizing the mobility data. These are two of the problems we have encountered during our talks with telecoms operators, but there are many others like TV, quality of experience, determination, call reduction, churn reduction, etc. So I will start by introducing the efficient network planning use case. I will give you the context of the problem, and then I will give the floor to my colleague Esther, who will describe the magic behind the algorithm. So this problem comes from the need for mobile operators to reduce the rental bill for their sites. Just to give you an idea, in a few years back, 2016, 2017, in the UK alone, there were around 52,000 mobile phone masts with an average rent of £5,000 for rural masts and over £11,000 for urban masts rent. So they have an incentive to use fewer, cheaper sites and reuse them, what we call as collocate them, whenever possible. It's a problem that network planners can solve optimally on a small scale and reasonably well on a large scale. However, given the volume, in order to find the optimal solution at a large scale, it's necessary to use algorithms. And for this, we have designed an algorithm that, given a set of sites and candidates in an area and certain capacity and coverage objectives, finds the network plan with the lowest cost for said area, meeting all the objectives, considering the use of new sites, new stations in existing sites, new cells, or cell extensions. So now I will let my colleague Esther Fernandez Bravo explain the mathematical apparatus on which this algorithm is based. So Esther, let me give you the control, and the floor is yours.
Thank you very much, Julio, and hello, everyone. I am Esther Fernandez Bravo, and thank you for joining us today. Let's move on, given some more detail about the use case that Julio has just presented. In order to have the complete picture of the problem, this figure here represents the information that is considered as input to the problem, and also the elements of the solution that the mathematical model developed will give. The rectangle above gathers all the input information, that is, the existing network plan that includes the existing nodes, that are the stations that allow the communication between the network and the users, the current capacity of these nodes, and the sites, which are the geographical locations where the nodes are deployed. Another input element is the link budget output, which is the balance between the power gains and losses. And this allows measuring the total power that reaches the receiver point from the transmitter point. The coverage footprint is also input information. And in other words, given the target area to cover, the target area that we want to plan, which is divided into square lots, the coverage footprint gives the lots that each node can cover in terms of traffic. We also have the traffic demand target for each lot, the capacity of the nodes, and finally, the CAPEX and OPEX costs, where CAPEX costs will be the investment costs defined for each site, node and cell, and OPEX costs are the operative costs that are defined for each active site and node. And we have two goals: to meet coverage and capacity requirements. And with these two goals, the algorithm that we have developed will propose a minimum cost network plan that will be found by taking some of the following actions. First of all, to open a new site in a new node. Second of all, to deploy a new node in an existing site. And finally, to upgrade the capacity of a cell when allowed. Here we have the representation of two states of the same target area before and after taking any of these decisions. We can see that in the image on the left, the green triangles represent already existing nodes, while the white triangles bordered in orange represent potential sites where new nodes could be deployed if necessary. The image on the left represents the initial congested state, represented in pink color, while the image on the right corresponds to the optimal state after the following actions have been carried out. 4 new sites are now open, each with a node on them, which are represented in dark green. 2 new nodes have been deployed in existing sites, represented in orange, and the capacity of a node has been upgraded, which is represented in dark blue. So these decisions that the algorithm has proposed are the ones that the mathematical model provides, attempting to minimize the overall cost while capacity and coverage objectives are met. And we can see in the image on the left that the implementation of this decision would reduce the congestion in the target area, ensuring that traffic demand is fulfilled. And after this brief introduction to the problem, the question should be, how is the mathematical principle behind prescriptive analytics applied to the network planning problem? Well, as we call it, the magic behind applying prescriptive analytics to this kind of problems is to be able to create the solution space that contains all the network plans that meet the conditions. And then, by exploring the solution space, pick the plan with the lowest cost. Naturally, this way of addressing problems is not possible for a human mind, especially when the target area to plan becomes to increase in size. So the application of prescriptive analytics to model the problem and the use of Gurobi solver to explore the plans and select the optimal one allows the efficient planning of telco networks. And before getting into the detailed mathematical formulation that I will present now, here comes a list of assumptions that are applicable to the model developed. First of all, we are considering an aggregating capacity of overlapping cells. And this means that given a lot, which is covered by several nodes, the total traffic demand covered will be the aggregation of the demand covered by each node. Second of all, we are not considering signal level for the sake of simplicity. And instead of that, we have defined a Boolean value covered, not covered, for each per lot cell. So for each lot, we have the information about the nodes that can be light by that node. Every square lot of the target area requires the same minimum signal level. We are not considering interference or channel allocation. And finally, site and node decommissioning are not decisions that the model will suggest, but they are obviously feasible actions to carry out. And now I will present the mathematical formulation of the mixed integral linear programming model we have built to address the efficient network planning problem. The input information of the scheme I presented before, which was the rectangle above, is mathematically represented by the parameters. There are binary parameters, like the three first ones, that represent which sites, nodes, and cells are active in the initial plan. And there is also another binary parameter, omega, which refers to the Boolean value of coverage. There are other continuous parameters, such as the ones related to costs, to traffic demand, and node capacity. The decisions that must be taken are mathematically represented by variables. As it is a milled model, there will be both binary variables that will indicate the nodes and sites which will be opened in the optimal state, as well as continuous variables for representing the capacity and the demand for each lot covered by each node. The model constraints allow taking into account the requirements that the new network plan should fulfill. The first block of 6 constraints provide relationships between the new and the existing network plan in terms of the sites and nodes that may be opened in the optimal state. There are other requirements in terms of the capacity that should be met and the node capacity that should not be exceeded. And of course, we also have constraints related to coverage, like the last 2 ones. On the one hand, we have to take into account that the aggregation of the demand fulfilled by one node for the loads that the node covers should not exceed the node capacity. And on the other hand, for each lot, the aggregation of the demand covered by all applicable nodes should be equal or superior to the traffic demanded by that lot. And finally, the goal of finding the minimum cost network plan is represented by the objective function, which is a combination of all the costs that are applicable to the network plan. And here we have the complete mathematical model. So by solving this model, we can have the actions that are required in terms of number of nodes and capacity to satisfy the coverage and capacity demand at the lowest cost. And once the solving approach and mathematical principles are clear, I am bringing you an example of a simple problem we have solved using this approach together with Guillermo solver. First, I will present the data we have used, then the results obtained, and finally, I will comment on 2 escalation techniques that could be applied to solve larger problems. This image here shows the area which network has been planned. It is a 4 square kilometer area with 16 4G existing sites and 3 cells per site. The image on the left represents the 4G traffic demand of the area, while the image on the right represents the location of the existing 4G nodes, colored in green, and also the location of some candidate sites where new nodes could be deployed, if needed, represented in blue color. We can also see the CAPEX costs that apply to the actions that can be carried out. We can see that opening a new site costs almost 29,000 credits. Deploying a new node, 37,000 credits. Installing a new cell is around 12,000 credits. And finally, agreeing the capacity of a cell is the cheapest investment, amounting to nearly 6,000 credits. So with this information, the algorithm will provide an optimized 4G network plan that will indicate the number of sites and nodes that need to be opened and the cells which capacity need to be upgraded in order to satisfy the traffic demand of the area with the minimal cost, given the costs that I have just explained. So as you can see, the initial 4G state is congested, and new nodes will need to be opened to satisfy capacity and coverage demand. It should be noted that this example is not using any output from a network planning tool, so it is just a simplified version to highlight the mathematics. And besides, the example is very underdimensioned. We're just considering a 4 square kilometer area. And for simplicity, cells can have half or full capacity, and all of them start at half capacity. So the decision of upgrading the cell capacity will mean doubling their current capacity. The algorithm allocates cell capacity to the nearest slots, and this is an approach that could also be refined by considering signal strength forecasts and by simulating power allocation algorithms. So after applying the optimization algorithm to the area that I have shown, this is the new network plan. We can see that the algorithm has proposed to increase the capacity in all cells, which was something that was expected due to the lower cost of this decision and the possibility to double the capacity in all cells. The algorithm has also proposed to build 5 new nodes in 5 new sites, which are represented in brown color in the figure. And as we had 8 candidate sites, there are 3 candidate sites that have been ignored. So no node has been built on them, as capacity and coverage are already satisfied with the 5 new nodes that have been deployed. We can also see that this plan has meant an increase in operating costs of over 5,000 credits and an investment of over 662,000 credits. It is the minimum cost network plan that satisfies all requirements. And once again, I want to remark that this is a very simplified example of the efficient network planning tool that can be solved with this approach. The example illustrates how the approach can be applied and the type of solution that one can get. But the algorithm is designed to solve larger and more complex problems. For example, this chart here represents 2 other instances of bigger size that have been solved with the model developed and the solver Guillermo. The first case corresponds to a 400 square kilometer area, 100 times bigger than the one presented in the previous example. This instance considers almost 8,000 sites, taking into account both the existing ones in the initial plan and the new candidate sites. And over 440,000 nodes are distributed throughout the target area. The implementation of the algorithm in this instance has provided a minimum cost network plan that satisfies all requirements, amounting to almost 400 million credits. And it is also interesting to remark that the algorithm solved for around 5 minutes and reached a solution with a 1.06% gap. The second case I have brought is a bit bigger, with a target area of 500 square kilometers and almost 10,000 sites, with over 555,000 nodes. In this case, the minimum cost network plan has a cost of 517.5 million credits. And the algorithm has reached the optimal solution for this case in 320 seconds. So we can see how the combination of Guillermo and the NIL model developed works quite well for this example. It is worth mentioning that normally the bigger the problem to solve, the more time it will require to reach a good solution. And what is more, if the case to solve becomes very big in size, then some escalation techniques may need to be combined with this current mathematical model to get good plans in reasonable computing times. The escalation techniques I am referring to can be both exact approaches, aiming at partitioning the problem into multiple smaller problems, such as the vendor decomposition technique, but also approximate approaches, mainly heuristics and methodistics, that do not ensure optimal solutions, but do speed a lot the process of finding reasonably satisfactory solutions. And finally, a couple of conclusions and highlights about the case that has been presented. First of all, I will remark that real-life network dimensioning and planning problems can be very hard to solve. So optimal solutions require using mathematical algorithms, as we have seen today. Second of all, the use of Guillermo built models in network optimization in the case presented allows inspecting the whole solution space and choosing the lowest cost plan that meets all requirements. So all in all, Guillermo enables fast problem solving that saves time and money for planners. And now I will give the floor to Guillermo, who will present the second case we have brought today, named Mobility Data Monetization in the Telco Industry. The floor is yours, Guillermo.
Thank you very much, Esther. In this use case, we will look at how mobility data from telecommunication companies can be monetized to improve the process of locating new electric vehicle charging stations. As in the previous case, I don't have the control. Let me request for it. 1 second. Now, as in the previous case, we will start by giving some context to the problem, and then we will be able to see the mathematical model and an example of the results obtained with it. Although there are tools that allow looking at the location of electrical vehicle charging stations, their status and availability, these tools are more useful for the end user who wants to plan a trip with an electric vehicle than for the person in charge to the expansion of a network of chargers. Since although they all allow knowing the number of electric vehicle chargers in a given area, they do not allow knowing what the real demand for these chargers is or the amount of cars that pass next to them and could be potential customers. Thus, the need arises to look for additional data sources and models to help the decision maker where these chargers should be located and what type they should be. In order to try to obtain an optimal solution to this problem, maximizing the demand met by the chargers, either by installing more charging stations or by upgrading the chargers to faster and higher power chargers. In order to solve this problem, the following relevant data sources are identified. First, we have identified that mobility data from a telecommunications operator. In this case, we have used the mobility data, In this case, we have used the mobility data from Orange, that is a telecommunications company here in Europe, through their product called FluxVision. FluxVision allows us to know the number of people that cross an area of interest, knowing also the origin of their travel and the destination. Also, we can know where they have their residence or where they have their activity area during the day. This data, we can get it by the hour, and that is going to also help us to know the peak hours of mobility through the study zones that we are going to set up. Then we also are going to need the historical data of the chargers done in other charging stations of the consumer. That way we can know the past charges and the energy consumed, and this will allow us to model the future demand of the new charging stations. For these charging stations, we are going to need the investment cost and the operating cost of running them. And also, we are going to use some public data from different sources. One source of this data is going to be the number of electrical vehicles in use, or the vehicles that have been registered, being in the country of the study or even in some areas of this country. In the case of Spain, we have this data by provinces. And then we also are going to need the mean amount of passengers that go in a vehicle. This is because the mobility data that we get from FluxVision only talks about people, not about vehicles. And then the output is going to be the location of the new charging stations, the type of chargers that are going to be in these charging stations, and a demand forecast of charges in these stations. As we can see here, FluxVision allows us to have a coverage area small enough near a motorway so that we can get only the people that are traveling through the motorway and not the people that are moving in the cities close by to the motorway. Finally, to tackle this problem, first we have to set up the target. The target could be the highways, the secondary roads, or the cities. We also have to know the blocking time or the queue time that we want to have in the charging stations and which are our peak hours. And then we have to set up our available budget to do the expansion. Once we have this target set, then we can pass to a nominal plan. In the nominal plan, we can identify the study areas that we want to focus on so we can get the mobility data from FluxVision. In these areas, then we have to find a more detailed plan and find the final possible locations for the charging stations that in a given study area could be more than one. Once we have all these areas and final places decided, then we have to model the return of the investment and the dimensioning of the stations, so that our optimization model can decide which areas should be prioritized and should have a charging station deployed first. To model the return of the investment, first we need to have a forecast of the demand of charging vehicles in a given zone. For this, we are going to use the mobility data that we have also for the current charging stations of the client. With that data and the historical data from the charges, we can find the relationship between the flow of people, or cars in this case, because we also know the average vehicle occupancy, to the relationship to the charges. That way we can have a forecast of the charges that are expected to be made in the new zones. We can also take into account different data, such as the utilities that we have on these zones, such as if we have a restaurant, because that could affect the amount of chargers, or if we have the presence of competition close by. With this forecast and the operating cost, then we are going to be able to know the return of the investment and to make the rollout plan for the new stations in the network. The mathematical model, as this use case was done for a Spanish company, we cannot show all the formulations. So I'm going to give a small example of part of the simulation and the assumptions of the model, and then I'm going to show you some results. So the assumptions of the model are that the investment cannot exceed the maximum budget, that the dimensioning of the charging station must consider the occupancy during the peak hours, that is between 10:30 and 12 in the morning and between 5:30 and 6:30 in the afternoon. These peak hours were found thanks to the mobility data and thanks to the historical charge data. Then the demand of a given study zone cannot depend on the demand of the nearby zones and the decision that we take for those zones, and because the client asks for it, that the minimum demand has to be covered. Also, the charging stations cannot have any configurations. So we have a set of types of stations that we can install. As we can see, the stations have a pretty big jump between the 100 kilowatt station and the 500 kilowatt station. This jump in investment cost and also in the need to access to a medium voltage network makes so that the 500 kilowatts station is more costly, and it has to be installed only in certain cases. So this model has a lot of binary variables, as you can see on the slide. We have first one binary variable that is going to tell us if we are going to assign a station to a given zone, and then another binary variable telling us which type of station we have to assign. Then we have a set of non-negative real variables that are going to help us calculate the investment in each one of the zones and the incomes that is going to be expected, so that our objective function can be to maximize the difference between the income and the investment. The constraints, as you all can imagine, when we have a lot of binary variables, are constraints to restrict the amount of values that the amount of times that these variables can take the value 1. First, by the station type that we want to assign, so that we only assign one type for a given zone as maximum. And if we assign one type, then we activate that zone. And finally, we have some constraints that also help to calculate all the investment and the income. So now I'm going to show some results of this proof of concept. This proof of concept was a study done over a 200-kilometer segment of a main Spanish highway, where we have 4 main locations with more than one study, with more than one final. We have 4 main areas of study with more than one location per area. Then we have an investment horizon of 10 years, a minimal demand coverage of an 80%, and we want to take into account 3 scenarios: 3.5, 5, and 6.5 electrical vehicle penetration. In our first scenario, we are only going to use 6 of the 8 possible locations to install a new charging station. These charging stations, 4 of them will be of 50 kilowatts and 2 of them of 100 kilowatts, and amounting to a total installed power of 400 kilowatts in total. As we can see, we cover the demand that we have as a minimum because that's a restriction of the model, and we have a small profit because the operating cost is very high. This operating cost is mainly because the cost of maintaining the installed power. As we increase the percentage of the electrical vehicles, we can see that we need more installed power and we start to have some losses on the profit, and we are not be able to break even. This is mainly because of the operating cost. And as we can see in the last scenario, in this case, we are forced to install a 5 kilowatt station in one of the locations, and that makes our operation cost and investment cost rise and not be able to have a profit. This inability to make a profit is mainly because of that station, because we have a lot of power installed there that takes a lot of investment, but the demand that covers that station is not high enough to be able to make a profit. As we can see in this slide, you can see the comparison between the three scenarios, and we can see how the supply operating cost, the supply cost doesn't increase that high, but the installed power operating cost is the one that is making us not be able to have a profit and break even in the 10-year horizon. So what we can take from this is that a higher electrical vehicle penetration does not mean higher profits, because the needs of and the costs of charging stations with more than 100 kilowatts are really high. We also have a high dependency on the forecast model, so that we can know what is going to be our demand of charges in each zone. If we have a better forecast model, what we could do is to plan a multi-year model when we have a basis scenario from which we can create different scenarios for each year that depend one another. That way we could try to find a robust solution for all these scenarios, and in that way, once time starts passing and we know in which scenario we are, we can know how our investment plans should roll out in the future. Finally, as you can see, real-life location problems can be very difficult because the amount of binary variables can get really high. In this case, as well, the use of data provided by telecom companies can help take better informed solutions for the problem. And in that way, it can help telecom companies open new revenue streams selling this data. Also, for these decisions, Gurobi helps us to model the problem solution, as Esther already pointed out, in a more quickly and efficiently way, saving both time and money for the decision maker. With this use case, the presentation of this use case is finished, and we can start with the Q&A.
Thank you very much, Guillermo. So now we can see there are a few questions. So let me take here. So there is a question from Alice Calamita regarding the first use case. Could you tell me which network planning tool do you use to calculate coverage? Well, in this one, we did not use raw data from the network planning tool. We used processed data. So it can come from anyone, from any network planning tool. In the end, what we need is for each lot in the algorithm, we need to know which cells of all the possible cells, the existing and the future cells, actually cover that lot. There is a question from Ashutosh. I don't know for which case this refers. It's how do you plan for a certainty in where future demand evolves? I guess this might be for either case. So Esther, Guillermo, do you feel like taking up this question?
Yeah, I can take it up. In the case for the electrical vehicles, as you said in the question, it could be a lot of uncertainty in the future because the market is not that evolved. That's why a multi-year model could help it, because we could have different scenarios with different evolutions, and we could have an investment plan that is trying to be robust for all those scenarios, so that we can know that our investment plan for now is good enough for a different set of scenarios that the system could evolve to. And I think in this case, it's very important because the market is evolving. There's not that many charging stations, at least in Spain, and that way the companies could have a plan, an investment plan, a rollout plan that could be more robust.
Thank you, Guillermo. There was another question from Akanksha about the first use case. Was there a need to solve the problem in less time? What if it would take 30 minutes to solve each case? Would it be acceptable? Well, Esther, before I give you the ground on this one, if I recall correctly, I think we never optimized for speed. So the results that we got were in the first iterations of the algorithm. Is that correct, Esther?
Yeah, totally. We got the results in the first iteration, and here we are not solving that big problems. As I was saying, the biggest problem that I have presented here is a 500 square kilometer area, but real problems may probably need to plan bigger areas, and in this case, time could be a problem. So the combination of milk models, Algorobi, would enable getting faster solutions.
However, from the network planning point of view, 500 square kilometers is already a sizable problem. I mean, it's a city the size of Madrid with 2 million people. It's already quite a big problem. And it's typically more than what a single network planner would take on, at least in an urban setting. In a suburban or in a rural setting, it would be different. But 500 square kilometers is already quite sizable.
Yeah, and another topic here, we have to take into account that the more time we give the algorithm to find a solution, the better the solution will probably be. So maybe we cannot find the optimal solution in the 5 or 10 minutes that we are solving, but if we give the model 30 minutes to solve, the gap to optimality will be reduced, and a better solution, a solution which is near to the optimal, could be obtained.
Okay, thank you, Esther. Another question from Ashutosh Kumar Thakur. I think this is for the second use case. How were the forecast and optimization models integrated? Guillermo?
So the forecast model will give us a forecast of the amount of energy that's going to be demanded in each study zone. And then the model is going to take that as an input, and is going to take into account how much demand it can cover based on the peak hour operation and the demand that is available, so that the model is going to decide the type of charging station that it has to install or deploy based on the capacity to cover that demand and the investment cost. So indeed, in this case, the forecast model is an input of the optimization model.
Thank you, Guillermo. There is another question from Hamid Mohammadi. Thank you for the presentation. What are the benefits of your cell planning algorithm over the existing ACP automatic cell planning algorithms in the planning tools like Atoll, etc.? Well, this does not replace Atoll. This complements Atoll. Of course, this tool does not calculate coverage. Coverage is an input, so it's interference of everything. So it uses the outputs from those tools in order to explore the solution space and find the cheapest network plan. Okay, there is one. I'm not sure I understand this one. There is question from Clifford. Are there confidence intervals and similar statistical forecast outputs as opposed to reaching optimality? I'm not sure to which use case this one refers, Clifford.
I think it's for the second one. I mean, depending on and I think this is what the question is aimed at. Depending on the forecast model that is going to be used, you could have the confidence interval of the forecast. So you could also try to incorporate that into the model. But in this case, we were using a forecast model that doesn't have a confidence interval, because there's no way to do them because they are based on decision trees. So that way we could not incorporate a confidence interval to the forecast for the optimization model to take into account.
Okay. Thank you, Guillermo. And there is another question for you as well. How is the customer data collected? How is the kilowatts hour during each charging data taken?
Julio,
Guillermo?
can you repeat? Can you repeat, because it was,
oh.
I didn't hear you, sorry.
Yes, sorry. How is the customer data collected? How is kilowatts hour during each charging data taken?
Okay, so the charger in the station is the one that is taking all the information. It takes the information, it can sometimes even take the information of the vehicle model, but not all the chargers do that. But all the chargers know how long the charging sessions were and how much energy was consumed by the car. So the owner of the charging station should be able to have that data available for it to be used. I saw that there was another question if there's available data for this, like public available data. Not that I know of, but maybe some companies are willing to sell the data about the chargers in their charging stations.
Thanks, Guille. There is another question from Francis Garuga. Just to clarify, the first use case is basically capacity plan, not really the network side design plan that takes place with the planning tool. Well, it combines both, because if the algorithm is fed with sites, also with new non-existing sites for which you have calculated the coverage and the capacity, and then you enter it into the algorithm, which selects the combination of sites with the lowest possible OPEX and CAPEX. So it combines a bit of both. It doesn't just do capacity because it allows for the addition of new nodes or in new sites. And there is a question, what meta-heuristic methods are used in use case one, Esther?
We have not used any meta-heuristic method in use case one. It was just a slide to show that the model that we have developed could be combined with a heuristic method if the model is not able to find a good solution in a reasonable time. And in fact, we have done some tests with the vendor decomposition, which was the other escalation technique I was talking about, which aimed at partitioning the problem. And this technique seems to work fine, but we have not done any tests with any methodistic method, but it could be great trying it.
Actually, there is a related question, now that you mentioned the vendor's decomposition, from Alice again. When you solved the biggest location problem, the one with 500 square kilometers, did you split the area in sub-areas in order to reduce the size of the problem, or did you solve it entirely? I think it's a good opportunity to mention the escalation techniques.
Yeah, the problem is that the bigger the area becomes, the more difficult it is to find a good solution in a reasonable time. So for the biggest instance, the vendor's decomposition was applied. And as I was saying, the idea is to split the problem into smaller problems and to solve a master problem, and with that solution to solve the second problem. And like that, it's like an iterative method to go improving the solution until a good solution is reached. So when big instances need to be solved, combining the mathematical formulation explained with this type of techniques works really fine.
Thanks, Esther. There's a question from Fabio about the second use case. Was there any technical legal reason why demand should be satisfied at least 80% in the second case?
There was not a technical or legal requirement. It was just one of the assumptions that the customer wanted to have. Actually, that in the model is used as a parameter. So in the proof of concept that we gave the client, they could choose to change that 80% to, let's say, 50%, 60%, and do different scenarios to see how that minimum coverage of demand will change their rollout plans and their investment plans. But it was just as a starting point, it was set up at that 80%.
If I may add to that, actually that's related to the probability of having to wait as a driver when you arrive to a charging point. So how likely would it be that all the charging bays would be taken when you needed to charge? And I think that's all for now, Silvana.
Yes, well, I want to really thank Baobab team for all of your explanations and the review of those two cases. And just to say, these are not the only challenges the telecommunication industry face. So there are many others that also mathematical optimization can help and can support and to find the optimal solution. So if you have any additional questions, not only about these two cases, but about the others, you can reach out to Baobab. You can see where you can find them, and also you can reach out to Gurobi as well. Thank you, everyone, and I hope to see everyone again in our next webinar. Thank you.